I'm Thomas Lund. I'm co-founder and head of analysis at DCUBED. My other co-founders are Dr. Thomas Sin, Alexander Tietz, and Joram Gruber. And also on the work going into this paper are my colleagues, Dr. Antonio Pedibellano and Ambara Harijoana, who are working day and night to make sure that we can actually accomplish what we set out to do at DCUBED. So some of you know us, some of you don't, and I'm going to go in starting from the basics of why we do what we do. Thank you, Barris, for that great intro for that one. And I'm preaching to the choir here, but we are in the middle of industrial transition. And the fundamental part of it is that we're transitioning from giant satellites to small ones, and from government agencies to businesses, and opening the door to more small institutional practices as well. And part of this transition, there's a lot of pains that come along with that. You need to have transitions up and down the supply chain to be able to enable hundreds of small satellites to be built instead of a single component for one big satellite. So what we're trying to do is we're trying to produce and develop off-the-shelf components that you can buy and receive in a matter of weeks instead of waiting months and months or even years of lead time for more complex subsystems. Now, the nitty-gritty of what we do is that everyone knows there's very little space under the fairing of the rocket, and you need to get everything as compact as possible. But not everything you want to do can fit in these tiny form factors, and definitely with PocketQubes that gets even more challenging. And here, obviously, some classic examples are communication antennas, solar arrays, drag sails for deorbiting as we get more and more space debris regulations coming into play. But all of these structures need to be a certain size or shape to actually do what they need to do, right? For any RF engineers, you need a certain shape of antenna to be able to get the performance that you need. And a solar array is a simple function of area to power. So there's a lot of applications, and there's a lot of new applications being developed constantly. For example, for sensitive instruments to be able to be deployed away from a spacecraft, everything needs to be deployed. It needs to be have some sort of motion initiated, and that's what we focus on at DCUBED. We want to make sure that when a systems engineer hears the word deployable structure, they're not going to start panicking. Instead, we want to uncomplicate the process, simple it down, and make sure that we have reliable, off-the-shelf deployable structures, so that you guys, the people that are actually building satellites and making these fantastic next generation missions happen, can do even more with what you want to achieve. So where we start is really with the critical enabling technology. These are the actuators. A lot of you guys use burn wires, I'm sure, but they're not so reliable, and it's always nice to be able to test the exact same hardware that you're going to fly. But up till now, the smallest actuator you can get, I think, is from the US, this tiny P5, which is still quite large, especially in a PocketQube. But in a CubeSat as well, it takes up a significant amount of space. And we're developing nano pin pullers and nano release nuts that can initiate this motion and release the deployable structures to be able to actually have a repeatable, reliable deployment and to test the same hardware that you send to space. So in these photos, you can see a little bit of the scale. They're really small, only 17 millimeters in each diameter. And we're also exploring scaling them up to bigger actuators, for example, for deployers. I know that's always an issue and a question for satellite integrators, is how you're actually going to get the satellite off the launch vehicle. So we're also developing a couple bigger actuators for that. But also we're looking at developing smaller actuators that are more tailored towards really picosatellite applications. But obviously, as you get smaller and smaller, the challenges become greater and greater. And then after that, this was sort of our initial, because you can't have a deployable structure if you don't have an actuator. But now we're at that stage where we have these actuators. We're now developing our first deployable structures. I know it's not the best word to say at this workshop, but we are focusing mostly on CubeSats. But all the technology that we do, we're always looking at scalability, both up and down. And our first two developments, the first one is a space selfie stick. This one is mostly for sort of troubleshooting, making sure that your satellite is operating correctly, making sure that your other larger deployable structures have deployed properly and in the right configuration, so that during the commissioning phase, you can really troubleshoot and narrow down to the problems quickly and effectively, because no matter how high quality your sensors are, a photograph is just worth so much more. And then our next stage of development, we're working on an 𝗖cie project for a solar array, which I'll talk a little bit more about later, which is a high power solar array with a very high packing efficiency. Now, across all of these products, we focus on a couple of key things to make sure that they're as usable as possible. And we're always looking for feedback and pilot customers to help us iterate in the design process itself, so that we can then make sure that the products that we build, because we want to make them off the shelf, we want as wide of an audience to be able to use them to enable their missions as possible. So one of the things we're leveraging for the actuators in particular is 3D printing. So you can see in the top picture, there's these extra legs sticking out. This is a 3D printed metal part. And these extra legs are just a different interface, because typically we use the 2 diagonal holes as the interface to mount it, but some customers need a slightly different interface for various reasons, and we want to be able to provide that. And 3D printing has helped us keep the same high quality product, everything qualified, and all we change is a little bit of the interface, and we don't need to requalify the product after that. So that's something that we really are interested in, is customizable mass products. And then the next one is just resettability and feedback indication. So all these actuators are resettable within 30 seconds. So you can test and repeat very quickly. Failing fast is not just a startup mantra, but it's really an effective strategy also in product development, so that we can get to meaningful results quickly. Finally, we're always thinking about you guys. We're trying to put ourselves in your shoes, and we're working with different pilot customers to make sure that each product that we produce, everything that we design, is specifically for nanosat and small sat needs, and picosat. And then finally, we're located in Germany, so we don't have any pesky American ITAR or EAR restrictions. There are a couple of export restrictions, but those are EU-wide, and I think they're not particularly extreme. So a little bit more. I mentioned already they're 17 millimeters. We like the little cube factor, so we go 17 by 17 by 17, and only 25 grams. But at that size, we have really huge performance of 50 newtons in terms of the direct side load that it can actuate under with our standard interface, which we can recommend and help you work through. We have substantial survival loads beyond that. And the temperature range, we've only been able to test down to -40, but theoretically we should be able to push that down to -65 as well for more extreme cases, but we haven't had a customer need for that yet. As I said, it's quick resettable, really handy to use. I forgot to prepare my demo unit to show you in person, but very fast, and we can reset it up to over 100 times. We've qualified it with extensive testing to make sure that's possible. Right now, if you order today, it's around 6 to 8 weeks before you can get one in your hand, but we're just transitioning into the true serial production, which means that in the very near future, hopefully by December, if you ordered, we could have one shipped off within 2 weeks, which is quite novel for any kind of space mechanism. And we're also gearing up for our first customer launch in January, as well as a parallel IOD mission in January at the same time on SpaceX flight. So yeah, a little bit more about the Space Selfie Stick. This was a project, it's actually on the IOD. We wanted to demonstrate the actuator's functionality, and we thought, well, how best to demonstrate an actuator's working, but with a deployable structure. So we very quickly went from our initial kickoff through to FM within only about 5-6 months from starting the design to being ready for flight. And that just goes to show our kind of quick turnaround time in developing these types of projects. We're really trying to speed up the space industry, and we want to work with you guys to be able to do that as best as possible. The camera we're using is just a simple off-the-shelf camera. It has a nice wide-angle lens, and we have a boom of 80 centimeters to be able to get the full spacecraft, and hopefully as well maybe the Earth and the Moon in the background. We'll see exactly what the quality of the photographs look like when we get them down during the IOD, but we're always looking to maintain the Pareto principle of 20% of the effort gets you 80% of the way there. And we think that with that 80%, we can do a lot. And so we can decrease a lot of costs in storage. We can increase reliability and the speed of turning around. And then we obviously work really closely with system providers to make sure that it's going to fit in a wide variety of systems. And then, as I mentioned before, we have this PowerQube 100-watt nanosat solar array. So the requirement for that is that it fits within a 1U volume, and not necessarily a 1U form factor, but we are looking at whether or not to do it in a single U component that you can stack on top, or just within the volume. And one of the key requirements is the market fit. So we have German Orbital Systems as our partner for this one, as a satellite integrator, to help us with making sure that it fits the market. But we're also looking for pilot customers and working with pilot customers to get their requirements and integrate those into the design process, so that by the end of the year, when we actually have our IOD launched in December of 2022, then we'll have an off-the-shelf product almost. We'll have to convert it from the design one-off into an actual serial production, but with that design locked, we should be able to meet a wide variety of applications and make sure that you guys aren't thinking in the 10 or 20 watt range, but in the up to 100 watt range, and you can do so much more with that much more power. The IOD mission for this is called PowerSat. We're doing it in cooperation with Cal Poly through the NASA ELANA program. So this should be launched at the end of next year or in the beginning of 2023. So again, for a complex subsystem, actually quite a fast turnaround from design through to launch. So I finished a little bit early here. But I guess that gives a little bit of time for questions. We're always looking for people to work with, always looking for new ideas and new concepts that we can develop and work together with. So yeah, thank you.